Today, we're going to delve into conditional probability and independence, and we will see how to calculate values with conditional probability. But first, we need to understand what we are talking about when we talk about conditional probability. Now, when we say conditional probability, when we talk about it, we are actually talking about two different stuff. One of those two concepts should be understood. First of all, we are either talking about some sort of situation where we know, where we have or partial knowledge about an experiment or a trial or something, some stochastics process, and we have that partial knowledge, and we can use that partial knowledge to derive probability value for something else, okay, for an event that is related to that partial knowledge. Or we can try to calculate some difficult probability for an event, for a difficult event, for a complex event. And we may try to break this event into a few pieces, two or more pieces, and try to calculate each probability value of those pieces and then put them back together to find the probability of the large event, that complex event. Now, it can either be we have partial knowledge, or we are trying to break down the complex event and calculate all the values one by one. Both of which is the it's part of the use of conditional probability. And when we talk about conditional probability, we are talking about at least three events, where one of them is the given event, the condition event, and the other one is the event that we are trying to calculate the probability of. Now, as you can see, we have E and F as two events, and then we write the conditional probability of E given F like this. Now, here, F is the given event. Now, the given event means when we talk about the first type of approach, we are talking about the partial knowledge that we have been given. We know that F is true, or we accept that F is true. F has happened, okay? It has occurred. We don't have any more say on this one. So when F has occurred, we are talking about the probability of E. So we know that F has happened. There's no going back from this one. So will E happen? What's the probability of E happening when F has happened? This is what we are talking about when we talk about conditional probability. Now, when F occurs, for E to occur, okay, when we talk about occurring, we are talking about outcomes, okay? Some outcome in F has happened, okay? One of the outcomes in that F event has happened. So if you want E to happen as well, that outcome should also be inside E, the set of E, okay? So we are looking for an outcome that is both E in E and in F. If you want E to happen, the outcome should be both in E and F. And we also know that F has happened, so the sample space has become equal to F. Okay, it has shrinked, it has been reduced to F, because any event or any outcome that is not in the event F hasn't happened, can't have been happened. Okay, it's impossible, because we already know that, as it was given to us as a partial knowledge, that F has happened. So anything outside of F is just stamped out. It's gone. We don't need them anymore. They're not relative anymore. Any outcome of F just makes up the sample space. Okay, all the outcomes of F make up the sample space now. So we call this new sample space a reduced sample space, which is made up of all the elements of F. All other elements are gone. Now, we are looking for an element that is both in E and F. It's in their intersection. And we know that our sample space is now F. So think about the probability, how the probability is calculated from last week. We are looking for a number of outcomes in all the outcomes in the sample space. So we just, divide them. So here it's the same thing. We are looking for the elements from the elements of F, so it's a reduced sample space. We are looking for elements that are both in E and F. So this condition probability, E given F, can be calculated with this ratio. The probability of E intersection F divided by the probability of F. So this will give us this probability. Now, we can apply this in any way we like. We can just switch those places and try to look for more meaning, and we can see it here very easily. So if E given F is written like this, then F given E will be written like this. As you can see, the only difference is in the denominator here. So instead of F, we have E here. So we can just, they both have a common numerator, which is the probability of EF. We can just take this common part and then make them equal to each other. So think about it. If we leave EF alone, okay, just leave EF alone, we have to take this probability of F and carry it over to the other side. We can do the same thing here, leave E times F, E and the probability of E intersection F alone, and just carry this probability of E here to the other side. Now, we know that these probabilities are the same thing. So whatever we have carried and created over here, the equations should be the same as well. So we can just say that these two parts have the same value. Simple enough. Now, we will use this knowledge later on. Just keep it on the side for now. So what can we do with condition probability? For example, an urn contains 10 white, 5 yellow, and 10 black balls. All right. A ball is chosen at random from the urn, and it is noted that it is not one of the black balls. So we have an urn with 25 balls. We pick a ball, and we say that it's not black. We don't know the color yet, but we know that it's not black. Okay. What's the probability that it is yellow? Now, from now on, we should start working with events all the time. Because from now on, you will be tempted to go back to your high school knowledge of probability and try to, create decision trees and stuff, which might be useful and which may give you the answer correctly, might happen, but it might also throw you off the track. And in complex questions, it will be useless totally, which you will see in here if you exercise and stuff. So you have to make sure that you get accustomed to using the notation of probability and events. So we have two events here. The first event is the probability we are looking for, that the ball we have chosen is yellow. I will denote this event as Y, the event that the ball selected is yellow. And then there's another event. The ball I have selected is not black. So it's B complementary. I will say that B is the event that the ball set is black. I could have written W and say that the ball set is white, but it's not useful here. We don't need that one here because we're not talking about any white balls yet. So I have only two events, and they're complementaries, of course. Y as the event that we have chosen yellow ball, and B, the event that we have chosen a black ball. Now, the question asked here is that we know we are given that the ball is not black, which is black complementary, and we are looking for the probability that it is yellow. So we are actually looking for the probability that it's yellow, given that the ball chosen is not black. Yellow, given that not black. This is the notation we are looking for. So we will just use the equation in the slide beforehand, and we will say that we are looking for the intersection of these two events divided by the probability of this event. So the intersection probability divided by the reduced sample space probability. Now, we know when we look at here that there are two events intersecting. Y, which is that the ball is yellow, and B complementary, which is that the ball is not black. Now, when we intersect two sets or two events, we can just check if one of them is subset or sub-event of the other. In here, Y is a subset or sub-event of B complementary, because B complementary says that you have yellow balls and white balls. Y says that you have yellow balls only. So yellow balls only is a subset of yellow and white balls. So we know that this intersection will become Y only. So it's going to be the probability of Y. On the other hand, the probability of picking a ball that is not white means that we are just eliminating all the, that's not black, means that we are eliminating all the black balls. So we have a total of 25 balls and we are looking for 15 balls only, which is 15 over 25, as we have written here. And here, number of Y balls over all the yellow balls over all the balls, which is 5 over 25. The 25s get simplified, the 5 over 15 gets simplified into 1 over 3. So we have a probability of 0.33333 of picking a yellow ball when we know that it's not a black ball. The ball we have chosen is not black. So this is how we calculate condition probability. We have to make sure that we can write the notation correctly. Now, in an exam, you will have two difficulties on that part. One of them will be defining the events correctly. The other one will be understanding the question correctly, the English part. If you can understand the question, the English part, then defining the events will be easier, of course, much easier, but still it can be a problem. To get rid of, get better at defining the events, you have to practice a lot. So I would recommend going into your books and, solving more questions, especially where you have to define events, and try to define events in questions that are, that don't need to define events, that are easy, that can be done without defining events. Still try to define events there, because defining events is something that you have to, work on a lot to get, a hang of it. Now, example 2. A student is taking a 1-hour time limit makeup exam. It's a 1-hour time limit, so after 1 hour, it's done. Suppose the probability that the student will finish the exam in less than x hours is x over 2, okay, for all x between 0 and 1. Given that the student is still working up to 0.75 hours, what's the conditional probability that the full hour is used? So we are in an exam, we have 1 hour to finish it, and the probability of finishing that exam in any given time, before that given time, for any peak time, is half of it. So, for example, my probability of finishing the exam in less than half an hour, which is 1 over 2, is 1 over 4, because x divided by 2, 1 over 2 divided by 2 is 1 over 4. So, whatever I, choose as an hour, any chance of finishing before that hour is half of it. So, when we're talking about the probability here, we are given that the student is still working up to 0.75 hours, which is 3 over 4. So my probability of finishing before 0.75 hours, which is, 3 over 4, was 3 over 8. So my probability of not finishing before it is 5 over 8, 1 minus 3 over 8. Just keep it in, somewhere safe. Now, the question is, we are still working up to 0.75 hours, which means that our x value, the time that we are going to finish the exam, is going to be greater than 0.75. That's a given. We know that. And we are looking for the probability that we will use the full hour. So x is going to be greater than 1. We know that x can't be greater than or equal to 1. We know that x can't be greater than 1 because it's going to end at 1. Okay, we don't have more than an hour. We have just 1 hour, but we can write it as x is greater than or equal to 1. It's the same thing as writing x is equal to 1. In here, we are better off writing greater than or equal to for generalization and some other stuff as well, but you're going to learn those in the 5th chapter, so we have ways to go there. But still, writing this as x is greater than or equal to 1 is better for generalization at least. So we are going to have to write this as, the notation will be like this, as you can see here. We know that x is already greater than 0.75 because we have wasted 0.75 hours with that exam. So we are already at that mark, so the turning will be greater than, okay, that value. And we are looking for, x being greater than 1. We have already spent 45 minutes. Are we going to spend an hour in this one? We are looking for this probability. So this condition probability, again, we will use the definition and the formula, and we will get this part. So this, as you can see, is again an intersection from the definition, and this one is the condition part, which comes over here. Now, this intersection, x is greater than 1, x is greater than 0.75. Again, we can see a subset here. X is greater than 1 is a subset of x is greater than 0.75. So this intersection will yield the probability of x is greater than or equal to 1. And here we already know that the probability of x being less than 0.75 was 3 over 8. We have talked about this because we know that here, as you can see, the probability that the student will finish the exam in less than x hours is x over 2. So if we write this the other way, like this, let's just write it. Probability of x is less than or equal to, or less than 0.75, doesn't really matter here, is equal to 3 over 8. We already know this one. So this is 1 minus this one. This value is 1 minus this one, so it's going to give us 5 over 8. And here, x is going to be greater than 1. Again, finishing the exam before the 1 hour limit, which is probability of x is less than 1, is equal to 1 over 2, because as you can see, x over 2. So this one will be equal to 1 over 2, which will give us a ratio of 4 over 5, which is 80%. So we have 80% chance of finishing the exam at the 1 hour mark when we have come 45 minutes, when we have already spent 45 minutes. So we can say with 80% certainty that we're going to waste 15 more minutes on that exam. We're going to use or 15 more minutes on that exam. So the next question is about balls again and urns. We have a total of n balls, which are going to be picked from R plus B balls. We have R red balls and B blue balls, and we are picking n balls out of them. All right, without replacement, okay. And we know that K of that n balls are blue. We have picked them, and K of them are blue. We have already done the experiment, and we are asked, what's the condition probability that the first ball chosen is blue? We don't know which one was the first one. We haven't, noted it. After we have picked them, we have counted them. We don't know which one was the blue, and we are asked, what's the probability of the first one being blue? So here we are gonna define two events again. The event B is gonna be the event that the first ball chosen was blue, and the event K, which was given to us, that out of n balls, the K are blue. So K of n balls are blue, are going to be the K event, and the first ball chosen is blue is going to be the B event. Now, the question that we're asked is, given that event K, what's the probability of event B? So B given K, the probability of B given K. If you can understand this event, notation here, you're not going to have any problems with it, hopefully. But this understanding that this question, this given, sentence here, the sentence that's given, is turned into the notation as, B given K is the crucial part. If you can get that, it's going to be easy. If you don't, you have to work on it a lot. Okay, you're not going to get it in the first time, most probably, unless you are extremely smart or a genius. But if you work on it, you're going to get it, okay? And getting that notation, the, transformation of notation, transformation from a sentence from a text into notation is the most crucial part here. So we have two events, as I said. The B event, where the first ball chosen is blue, and the K event, where K of n balls are blue. And we are looking for B given K. Now, as we're looking for B given K, we have to just open it up using the formula, definition of the formula. And we know that it's the, intersection over the condition. Now, this intersection cannot be calculated. There are no subsets here. B is not a subset of K, K is not a subset of B, and we cannot calculate this intersection easily. So what we have to do is use the reverse version of that condition. So we are looking for B given K, but I said that, okay, maybe I can come up with something about K given B. So I'm looking for K given B times B. Probability of K given B times probability of B, because this is equal to this one. We already know that from the definition. So we're going to use this one. Now, as you can see, instead of the condition probability of B given K, we are going to use the condition probability of K given B times the probability of B divided by probability of K. Get used to this, transformation, because you're going to have to do it a lot, most probably, because most of the questions will require transformation like this one. So we already know that getting K, blue balls out of n balls when you pick them from R plus B balls is equal to this one. We have already used these combination formulas last week. So we are looking for K blue balls. We have B blue balls in total, R red balls in total, and we are picking n balls, which means that we want to pick K blue balls out of B balls, n minus K red balls out of R balls, which is going to be divided. This is what we want. This is the outcomes that we want, which is going to be divided by all the outcomes, the sample space, which is B plus R, and choose B plus R. It's, read like that, pronounced like that, I think, but still, combination of B plus R to N. So we are going to choose N balls out of B plus R balls. This is K, the event K, probability of event K. We are also looking for the probability of K given B. Now in K given B, we know that the first ball chosen was blue. So we can just remove it from the question. Pick a blue ball, remove it from the question. Now, what we have left is B plus R minus 1 balls. We're going to pick N minus 1 balls out of them. And we are trying to pick B minus 1 blue balls. K minus 1 blue balls out of B minus 1 blue balls. And again, N minus K red balls out of R red balls. Now we can write this as here. This is the same formula, except that we have reduced the number of blue balls by 1. But they are the same formula nevertheless. Okay, we just removed 1 blue ball and rewritten the formula like this one. And also, we are going to have to look for the probability of picking the first ball as blue. So PB, probability of B. Now, we are picking the first ball. We have B plus R balls again, and we're going to pick 1 ball out of this one. And this one has to be blue. This is easy. It's like, you have 5 blue balls, 10 red balls. What's the probability of picking a blue ball? 5 over 15. Okay, the total 5 divided by the total. Same here, B over B plus 1 R. Now, when we take all these equations and put them in this formula, they will just, the combinations will just be simplified. We will open the parentheses, get out all the, factorial values, simplify the factorial values, etc. We're going to do all the mathematics there, and we're going to get K over N, which is extremely simple when you take a look at it. Okay, again, when we want to solve a question like this, we need to pick the right events, and the events are usually hinted in the question part, in the question sentence, okay? Not in the whole problem, most probably, but in the question sentence. You're gonna have to find a few events there because, question will be asking you a probability, and the probability will be, taken from those sentences. So the probability asking question is here. Given that K of N balls are blue. Now, it says a given that. We're done. This is the condition. This is the event. K of N balls are blue. We are done with one event. This has to be an event. It cannot be, anything else. So we are saying that K of N balls are blue. This is an event. And yes, we have just given it capital K. This is an event now. What's the condition probability that the first ball chosen is blue? Again, condition probability that we are finding an event again. The first ball chosen is blue. Another event right here. And this is how you find them. Okay. From the sentence. Okay. When it says given that, it's talking about the condition. When it says what's the condition probability that, it's talking about the probability we are looking for. But they are both events. So as you can see, K of N balls are blue, an event. First ball chosen is blue, another event. So we are looking for, this is a given one, so B, K, B given K. This is what we are looking for. And then after we have written this one, we can try to find more events if there are more events to be found, if they are needed. It's not needed here. There will be an exam, there will be a question example where you can see that there's a third event as well, but still, we don't need it in this one. So after that one, we're just going to do the iterations, the calculations. Now, we have another way of actually, finding this probability, which is actually easier math-wise because there are less calculations, less operations to be made. We can say that we have a sample space, okay, K blue and N minus K red balls. We all know them. So this is the reduced sample space. We are just gonna permute those, just order those. So think about it. We already have a total of N balls, okay? K of them are blue. And we are saying that we are gonna just order these balls. And we're gonna count the number of, possible orders where the first one is a blue one. Simple. Pick a blue ball. There are K different versions of doing this. Pick one of the blue balls and put it on the, first point. And then you will have N minus 1 balls left. Permute them. N minus 1 factorial. They are all different balls. Blues and reds are different. You can accept it like this right now. No problem with that. And just permute them. N minus 1 factorial balls. And then what you have to do is just, divide it by N factorial, which is all the permutations possible with N balls. So what you're gonna get here is, after simplification, is K over M again. It's the same thing. Example 4. Suppose that an urn contains 8 red balls and 4 white balls. We draw 2 balls from the urn without replacement. Okay. What's the probability that both balls drawn are red? Now, there are 2 ways of doing this one. The first one is what we have seen last week. Just make the combinations. Just use the combinations. We are looking for 2 balls out of 12 balls. So 12 choose 2. Okay, and choose K. 12 choose 2. We are going to choose 2 balls out of 12 balls. 12 choose 2. Then we're going to say that we are looking for the outcome of 2 red balls out of 8 red balls. So we're going to choose 2 out of 8. 8 choose 2. So we're just going to divide these 2 values. Okay, this is what we have seen last week. But we want to make it a bit more conditional probability-like. We're going to say that, I had said it last week, if you remember, choosing them at the same time and choosing them one by one without replacement is the same thing, actually. Okay, you can just choose them one by one as well. So let's just choose them one by one. When we pick the first ball, it's going to be red. So we're going to call, we have all the defined events, R1 and R2. R1 is choosing a red ball in the first event, pick, and R2 is choosing an event on the second pick. So we are going to find the probability of R1, picking something red in the first pick. It's easy, 8 over 12. We have 8 red balls, 12 balls, 8 over 12. And then we know that we have picked a red in the first pick. So what's the probability of second, red in the second pick? Now we are going to remove 1 red ball from the, game, from the urn. We have left with 7 red balls out of 11 total balls. So it's 7 out of 11. But it's written like this. We know we are already given the condition that the first ball is a red ball. It was chosen. It's out of the game. And we are choosing the second ball as a red ball again. These 2 things are the same. We already know that they are the same from the definition, from the formula of the definition, because we know that this one is written as, R2 given R1 is written as the intersection of probability intersection of R2, R1 over the probability of R1. So these 2 are the same, and they are the same. As when it's calculated, they become the same thing. So they give out the same value. So we can either go with a combination or with the conditional probability. They are going to both give the same results. As I said before, one of them might be more viable, easier, or in an example, the other one might not be. You have to, be efficient with both of them as much as you can. And then we have the basis formula. Now, we're going to use this formula a lot, as you will see later on. But to start with this one, we have to remember a few set rules. The first one is the set E can be defined. The set and event are the same thing. As you can remember, set theory is very close to probability theory. The set E can be defined as intersection of E and F, union of intersection of E and F complementary. Now, if you remember this one, you can just put probability on all of them. This probability of E is probability of EF plus probability of EFC. So from here, we already know that this ENF and ENFC, they can be rewritten or transformed into conditional probability, some sort of conditional probability notation. We already know that from the first slides that EF can be rewritten as E given F times F. We also know that EFC, EF complementary, can be written as E given FC times FC. Now, these 2, these 2 can be transformed into these 2. We already know that from the formula. So, as you can see, any event E can be conditioned on another event. Now, as you can see, the probability of E, this is actually the second approach. Remember 2 approaches I have talked about? This is useful for the second approach. We had said that in the first one, we have partial knowledge and we are using that knowledge to derive a probability value. In the second one, we are trying to just break up a large or a complex event which cannot be easily calculated into smaller events which can be smaller events which can be calculated, whose probability can be calculated easily. Now, in here we have PE. This E value, this E event is complex, so we are trying to break it down into smaller, spaces, smaller events. In here, we are saying that we know that F has happened. So what's the probability of E happening now? A smaller portion of E. And in here, we are saying that F hasn't happened. So what's the probability of E happening again? Now, when we put these two probabilities together, we're going to get the probability of the event, the complex E event. So this formula is extremely useful and will be used heavily in this part, as you will see in a few moments, minutes hopefully. Now, this formula, A given B, we have already found out this one because we have already used it before over here somewhere. Let's go back over here. As you can see, we have already used this formula and we had seen it, how it was derived in the first slides. And now we are adding that we can use this one as well. And we can express this B value conditioned on the A value, the event, the B event conditioned on the A event. So we can write, instead of PB, B given A times A plus B given A complementary times A complementary. Now, as you can see here, this or this one is the same as this one. These two, are the same. So the number of probabilities we have to calculate is not that large. Okay, there are only 4 pieces that you want to find out about. B given A, B given A complementary, A complementary. These 4 probability values have to be calculated to find out the probability of A given B. Now, for example, an insurance company believes that people can be divided into 2 classes, those who are accident prone and those who are not. Okay, we have 2 classes. Their statistics show that an accident prone person will have an accident at some time within a fixed 1-year period with probability of 0.4. Okay, if you're an accident prone person in a 1-year period, you're going to have an accident with 40% probability. Okay, whereas this probability decreases to 0.2 for a non-accident prone person. If you're not accident prone, your probability of making an accident in a year is 0.2. All right, we assume that 30% of the population is accident prone. What's the probability that, okay, this part is important as well, 30% is accident prone. What's the probability that, okay, here comes the question and we have to find the events in here. What's the probability that a new policyholder is accident prone? Okay, this is the probability part, not the given part, the one we are being asked. So, new policyholder is accident prone. This is an event. Let's call this A. If is the same as given. We can write if or given. They both state the condition. If she had an accident, she had an accident within a year of purchasing a policy. Okay, having an accident in the first year. So we're going to call this one 1. I'm going to use a number to show this one instead of a letter. We usually use letters, but I'm going to use a number on this one because 1 is 1 year. Okay, having an accident in 1 year. So what we are being asked is A given 1. Event A given event 1. The probability of this one. So let's just write it. A given 1. We're going to use the Bayes theorem, Bayes formula. Now we know that A given 1 can be written like this, and this can become like this one from the Bayes theorem, Bayes formula. Now in here, 1 given A times A, probability of 1 given A times probability of A, and probability of 1 given A complementary times probability of A complementary. Now let's start with these 3 values or 2 values, PA and PA complementary. Probability of A and probability of A complementary. We already know that probability A is 30%. Because it is given us here. We assume that 30% of the population is accident prone. So policyholder is accident prone is 30% because he's one of the population. And AC is 70%. So 0.3, 0.3, 0.7, done. 3 values are gone, or 2 values because 2 are the same. Then we are looking for 1 given A. Having an accident in 1 year if you're accident prone. Okay, it's given here as well. So 0.4. It says that if you are accident prone, you're going to have an accident in 1 year with 0.4 probability. So 0.4 here, 0.4 here as well. and one given A complementary. If you're not accident prone, having an accident in 1 year, which is like 20%, 0.2, comes over here. So we just calculate the probabilities and find out that the probability of being an accident prone person, okay, if you had an accident in 1 year, is 0.46. Okay, that's okay, no problems there. At a certain stage of criminal investigation, the inspector in charge is 60% convinced of the guilt of a certain suspect. Okay. Suppose now that a new piece of evidence that shows that the criminal has a certain characteristic, such as left-handedness, flaming red hair, etc., is uncovered. If only 20% of the population has this characteristic, how certain of the guilt of the suspect should the inspector now be? Okay, this one is a bit harder event-wise. Now, we're going to say that one of, as you can see, here, the given event is that the population has this characteristic, but it's not really the given event. How certain the guilt of the suspect should the inspector now be? This is a bit vague, okay? This is a bit vague. We are looking for something like this in here. We know that there's an evidence that comes up that shows that the real guilty person should be left-handed, for example. We don't know if this person is left-handed or not yet. We're going to do the test and we're going to find out. But if he's left-handed, how sure should we be? This is the question we are being asked here. If he is left-handed, how sure should we be? Okay, this is the question being asked. So if he's left-handed, okay, he possesses the characteristic, event C. And how guilty is he, event G? Okay, so if he possesses the characteristic, how sure should we be? G given C. This is what we are looking for, okay? If he has the characteristic, how sure should we become? Now, the suspect is guilty, event G, and suspect possesses the characteristic is event C, G given C. Now, we have to use Bayes again and transform it into this one. And from here, we can just find the values. For example, probability of guilty right now without the characteristic is 60%. This is how we believe. He's guilty 60%. Okay, we believe that he is guilty, but this belief is only 60%. Then, if he's guilty, what's the probability of him having the characteristic? That's 1. Because if he's guilty, then he has to have that characteristic. He has to be left-handed because we know that the guilty person is left-handed for sure. So if he's guilty, if the suspect is guilty, suspect is the criminal, then he has to be left-handed. So this is 1. Okay. Again, we write the same values in here because they are the same thing. And then we're looking for this one. What's the probability that he's not guilty at this state? 0.4. Okay. And what's the probability that if he's not guilty, what's the probability that he has the characteristic? Okay, if he's not guilty, he's one of the population, so the population is a 1/5, 20% chance of having that characteristic. So he will have that characteristic with 0.2 probability. So 0.2 again. When we calculate these values, we're going to find the probability of him being guilty if he possesses that characteristic, which is 0.88, 88%. So from 60%, it comes up to 88%, the probability of the guy being guilty if he possesses that characteristic, left-handedness. Okay. As I said, in this one, taking the events from the question itself is harder. We have to transform the question in our head. It's actually asking something like this. Yes, it's asking like this, something like this. Now, we have the odds of an event. We usually don't go into odds of an event because we don't use, those in this class mostly, but this is something like general knowledge, okay? Odds of an event is useful for betting sites and any kind of bets, actually. So, for example, the odds of an event A is defined by the probability of A occurring over the probability of A not occurring, okay? Or the complement of A occurring. This is the odds of A. For example, if A has a probability of 2/3, 66% of occurring, then the odds of A is 2, because the probability of A not occurring is 1/3. So 2/3 divided by 1/3 is 2. We usually don't use the odds notation, but in case there's a question talking about the odds, it's talking about this one, okay? This division. So, example 7. Again, we're not going to use odds that much. When coin A is flipped, it comes up heads with probability 1/4. Okay, it's a deaded coin. It's, it's not a fair coin. Whereas when coin B, loaded coin, whereas coin B is flipped, it comes up heads with probability 3/4. Again, not a fair coin. It's a loaded coin once again. Suppose that one of these coins is randomly chosen, is flipped twice. Okay, pick a coin, flip it twice. If both flips land heads, okay, we are given a condition here. Both flips land heads. Okay, what's the probability that coin B was the one flipped? Okay, again, the question. This is not the condition, but this is the question here. Probability that coin B was flipped. Now, here we are talking about picking the coin. Flipping the coin is the same as picking the coin. There's no difference in that. The event is, the first event is, the condition event is H. We're going to call it H. And this event represents that two of the flips, both of them actually, has come up heads. We know that already. This is the condition. And then we're going to pick the events of using coin B as B. So we're looking for B given H. Okay? We already know that two heads have come up. We are looking for the probability of having picked coin B. Now, B given H, again, we're going to use the bias, and it's going to be something like this. Okay, we're going to just open it up with the bias. As you can see, B given H is H given B times B over PH. Now, H given B, flipping it twice and getting both of them heads when we are using coin B. That's easy. One is getting one, heads is 3/4. The probability is 3/4. Getting two heads is, this is squared, so 9/16. 9/16. Picking B, that's 1/2 because there are two coins, they are chosen randomly, they have the same probability, so it's 1/2. And then PH, getting two heads in a row. Now we have to open up this one. Getting two heads in a row using coin B, getting two heads in a row not using coin B or using coin A, same thing, because. So we already know this one is equal to this one, so we have to calculate this one. Getting two heads when not using coin B. Well, with coin A, it's 1/16, 1/4 squared. And choosing or not choosing coin B is 1/2, which is equal to choosing A. So the calculation yields us 9/10, 90%. We are 90% sure that we are using coin B. If we get two heads in a row, then we are using coin B. This is what it says to us. Now, this one is a bit more, game-like, let's say, a bit different. And there is a very good question at the end of this part, Monty Hall question, which you will see. It resembles that one as well a bit. In, thinking-wise, let's say. Suppose that we have three cards, identical in form, except that both sides of the first card are colored red, red. Both sides of the second card are colored black, black. And one side of the third card is colored red, and the other side is black, so red, black. The three cards are mixed up in a hat, and one card is randomly selected and put down on the ground. If the upper side of the chosen card is colored red, we don't know the other side. What's the probability that the other side is colored black? So, any ideas? What's the probability of the other side being black? Is it 1/2, 1/3, 2/3? Any ideas? Okay, no ideas, I guess. Let's just think about this one in terms of, notation, conditional probability notation. We have three events, actually four events here. The one event is seeing that the top side is red. Okay, this is the event R. Top side is red. We know this one already. Then the three events are: the card is either red, which we call RR, red blue, RB, or red black, sorry, RB, or black BB. These are the four events. Now, what I'm looking for is the probability that this card is red-black, given that I have seen the red. So RB given R. I'm looking for this set. So in here, I'm going to have to just open it up with bias as usual. So we are looking for this probability. We're just going to open it up. But as you can see, we can just replace, these two. So the condition probability will change. The condition will become RB. This will be the same. But in here, we are looking for the probability of R. Now we have to divide this R into its three conditions. Okay. In the first condition, we have chosen RB, red blank, and we are looking for R. We have chosen RR, and we are looking for R. We have chosen BB, and we are looking for R. Now, this is easy because this is 0. You cannot see a red side on the top with two black sides when the card is two black sides. So this is 0. We don't need to check this one. In here, when both sides are R, the probability of getting an R is 1, because whatever you do, it's 1. And getting both of, getting that card is 1/3. Getting RB is 1/3. When you have RB, getting R on the top side is 1/2. So when you write all these values and you calculate them, you get the probability 1/3. So, independent events. Knowing that F has occurred generally changes the chances of E's occurrence. Now, this part is about two events affecting or not affecting each other in case of independence. In special cases where E given F does in fact equal to PE, so the condition probability doesn't change the real probability. P is equal to E given F. This means that F is not affecting E, no effect at all. So we can, it doesn't matter whether F has occurred or not, the probability of E is gonna still be the same. So when we know this, we can just write it like this. E given F, which is written like this, is equal to PE. Now, as you can see from here, from the right-hand side, we can see that we can just take PF and carry it over next to PE, and we will get this formula, which you have seen last week. We had talked about this, the simple version of it. So there is EF, the intersection of EF, probability of intersection of EF, is equal to PE times PF. When this happens, we can just say that, okay, E and F are independent. It doesn't matter if F has happened or not. P and F are independent, and we're done there. All right? So we keep going with the example. A card is selected at random from an ordinary deck of 52 playing cards. If E is the event that the selected card is an ace, and F is the event that it's a spade, then show that E and F are independent. Now, in this question, we have, again, two events, okay? And they are given to us. One of them is that the card is an ace. So we are picking one card out of 52 cards, and there are 4 aces in there. So the probability of PE, the probability of event E, is 4/52, which is 1/13. It's obvious. And for F, there are 13 spades, because the deck has 4 suites, and spade is one of those suites, and it has 13 cards in them. So it's 13/52, which is 1/4. And then we need to show the independency, which means that we need to show that the intersection of these two events is equal to the multiplication of their, probability of intersection of these events is equal to the multiplication of their respective probabilities. Now, we all know that their probabilities are 1/4 and 1/13. You can stay there. And for EF, for the intersection, we want the card to be the spade ace, the ace of spades. So for the ace of spades, there's only one ace of spades in 52 cards, so it's 1/52. When we multiply 1/4 with 1/13, we again get 1/52, which shows that E and F are independent because these two values are equal. So if E and F are independent, so are E and FC, F complementary. This is actually an easy proof, because if we know that E and F are independent, we can just write this one, because we already know this one. This does not have to be independent one. We can gather that from here with E and F, the intersection of E and F can be opened up as like this. Let's just write it. We know that PEF is equal to PEF. So instead of this one, we're going to write this one. And then when we have written this one, we can just take that value and use this value as well. For example, we already know that this one can be just sent to the left side, and this value will be left alone, EFC. So in here, we will just write instead of this one, P, E, P, F. And then in here, as you can see, we now have this minus P, E, P, F. And if you take this into parentheses of probability of E, we have 1 minus PF, which is, again, as you can see, equal to this one. And this one is equal to the probability of F complementary. 1 minus probability of F is equal to the probability of F complementary. So we can already see that the probability of intersection of E and F complementary is equal to the probability of E times probability of F complementary, which is the definition of independence. So if E and F are independent, then E and FC are independent as well. We can see it from here. This is again a simple, proof, a simple proposition. Well, what about 3 events? What if we had 3 events? Now, if we had 3 events, then all 3 of them had to be independent of each other. And they have to be independent of altogether. For example, when we have 3 events E, F, and G, we are expecting the intersection of EFG, probability of intersection of EFG, to be equal to PE, PF, PG, probability of E, probability of F, and probability of G. And we also expect all of them to be independent, pairwise independent. This also applies to more than 3 events, but we will not see more than 3 events that easily because it's going to take a long time to prove that they are independent. Because imagine it, with 4 events, you have 1 plus 4 plus 6, 11 different, equations to prove. With, even 3 events, there are 4 equations to prove, 11 equations. And with 5 events, it will be like, I don't know, 1 plus 5 plus 10 plus 15, goes on like this, I think. So it's a lot. So we don't need to go into those details because there are lots of equations. Usually 3 events is more than enough. If we want multiple events, 3 is more than enough. So we have an infinite sequence of independent trials to be performed. Now, the important part is that the trials are independent. You keep restarting each trial. They are not, they are not affecting each other. Each trial results in a success with probability P and failure with probability 1 minus P. We had talked about this stuff before in the last week, actually, and we had said that in those kinds of trials, there's a special name for them. It's binomial, distribution, and these trials have a set formula that represent them. We will remember it here, but still, what's the probability that at least 1 success occurs in the first n trials? So we're talking about n trials, not the infinite sequence, but just the first n trial. We'll need at least 1 success. Now, at least 1 success means that we can just look for the instant where there are no successes and find the probability for that no success situation and then remove it from 1, okay? Subtract it from 1. Now, what we need to do is make sure that all the trials, all n trials fail, okay? What's the probability of failing? 1 minus p, as you can see here. What's the probability that all n trials fail? The nth power of 1 minus p. So we just subtract it from 1. 1 minus nth power of 1 minus p. Done. What about b? Exactly k successes occur in the first n trials. Now, when we're talking about k success, exactly k successes, we're actually talking about picking those successes out of n. So we need to choose k items, k trials out of n trials, and say that, okay, these are the successful ones. So n choose k, combination of n and k. And then we need to make sure that they show the probability. They can, their probability can be shown as well, which is going to be p for 1 trial, for 1 successful trial. So kth power of p, kth power of p for k number of successes. And then we're going to have to show the failures as well. Because if we have k successes, we have n minus k failures. So the probability of failure is 1 minus p. So n minus kth power of 1 minus p. And when we add all of these together, as you can see here, we're going to get this formula. N choose k, kth power of p, and n minus kth power of 1 minus p. Now, this, you will see the PMF of binomial, but still binomial distribution, but still binomial random variable, but still, we're going to see this one later on. but we know how to drive it, how to, you know, find it out, find about it. But still, we're going to see it after the exam, most probably. And then the last one, all trials result in success. Infinitely many trials resulting in success. Okay, when you say all trials, you're talking about the limit of n going to infinity. So we know that each trial has a success of p, success probability of p, success rate of p, and this p can be taken, you know, can be multiplied with itself as many times as you want, and we want it to be multiplied infinitely many times with itself. Okay, that's too much. P to the power of n, okay, nth power of p, when n goes to infinity. We already know that if the value of p is less than 1 and greater than 0, this value is going to be 0. Because any value between those two, like for example, 0.9 to the power of infinity, it's 0. The only difference, the only, you know, value that's not 0, that gives us, you know, something other than 0, is 1. When the probability of success is 1, when the success is guaranteed, then all the trials will be success. We can say that easily. Normally, the infinite, you know, when we take the power, infinite power of 1, we say that, okay, it's unknown, we can't know. It's not really mathematically stable. But in here, we can say that it's 1. Because we know that when the probability is 1, okay, this is not a stochastic situation anymore. It's a deterministic situation. We know that it's going to happen no matter what. So even if we do this infinitely many times, this trial, they will all be successes anyway. So if p is 1, then the success of infinitely many trials is going to be 1 as well. Probability of success of infinitely many trials is going to be 1 as well. This is how we expect it, accept it at least. And now, conditioning on the first trial. Now, this part is extremely useful, actually, because it helps us, especially with the second approach, where we have a probability value. We don't have any, you know, partial information, but we want to find the probability of some complex events that we cannot really, you know, just calculate at an instant. So we have to take it apart. This is very useful in this taking apart part. Now, for example, we are gonna condition on the first trial. This means that we are doing many trials, more than one trial, and we are trying to model all these trials by conditioning them on the first one. How can we do that? For example, let's start with the example, and it will be easy to understand. Independent trials consisting of rolling a pair of paired dice are performed. What is the probability that an outcome of 5 appears before an outcome of 7, when the outcome of a roll is the sum of the dice? Okay, we are rolling 2 dice. Okay, and we are trying to see 5 come up before 7. We want to see that 5 comes up before 7. We are talking about the probability of this one happening. Okay, how can we find this one? There are 2 different ways, actually. One is easier, but it's not applicable all the time. I will talk about it later on. The other one is conditioning on the first trial. A bit harder, of course, but still applicable generally. Now, with 5 appearing before 7, we have actually, on the first trial, we have 3 different results. We can say that on the first trial, on the first roll, we have seen a 5. Okay. Again, on the first roll, we have seen a 7. Okay. And on the first roll, we have seen something other than 5 and 7. What that isn't important. It can be 2, it can be 6, it can be 12, whatever. They're all the same to me because they're not 5 or 7. What I'm looking for is only 5 and 7. The other results are not important to me. So yeah, I can just, you know, take them up into one event. They can say that, okay, anything other than 5 and 7 is an event. So rolling 5 at the first trial is an event. Rolling 7 at the first trial is an event. Rolling anything else at the first trial is another event. 3 events up till now. And there's a 4th event as well. 5 appearing before 7. This is what I'm looking for. Let's call this E. I'm looking for the probability of E, a 5 appearing before 7. Now, think of the formula for, you know, conditioning on another event, conditioning an event on another event. Remember, it is something like this. Let's just write it so that you can remember. For example, when we said PA is equal to PA given B, put a slight equal to, nice, A given B PB plus P A given B complementary P B complementary. Remember this one? Now, we can improve this into 3, 4, 5 or more events easily. As long as all these events, instead of B and B complementary, anything we write must have, must be mutually exclusive and sum up to the sample space, the universal set, if you wish. So we can write it like this. PA is actually equal to PA given B times PB plus PA given C PC plus PA given D PD. As long as we can write this, as long as we know B, C, and D are mutually exclusive and their union gives us a sample space, okay? As long as we know this, we can write it like this as well. Then, okay, as we know these hold all the time, then we can say that, okay, I'm going to condition on the first trial. And when I'm going to condition on the first trial, I'm going to say that the first trial can show up 5, the first trial can show up 7, the first trial can be something else. So I can just write for E, condition on the first trial. Now, this is E, this is F, this is G, this is H. I want to define all the events. And then I say, I'm going to write E in terms of F, G, and H. Because F, G, and H are the, sample space. They sum up the universal set, and they are mutually exclusive. If 5 has come, 7 can't come. If either 5 or 7 has come, something else cannot come. So E, G, and H are mutually exclusive. Now, I'm going to write PE, probability of E is equal to E given F times F, E given G times G, and E given H times H. Now, I can find values on all these, events and conditional events. Now, start with E given F. Now, F says that first trial is 5, okay? E is looking for 5 appear before 7. That has already happened, thanks to F. So it's 1, probability is 1. PF, 5, the first trial is 5, that's 4 over 36, so 1 times 4 over 36. E given G. G's first trial is 7, okay? E is looking for 5 before 7, not gonna happen because first trial is 7, so this is a probability of 0, 0. The probability of G is 6 over 36, but it's not important because it's gonna be multiplied by 0 anyway. Still, we have to, write it. And then E given H. I'm gonna skip this one. H. Now, H is easy. Probability of H is easy. Anything other than 5 or 7. Anything other than 5 or 7 means that you just subtract the probability of 5 and 7 from 1. And these are 4 over 36 and 6 over 36, which is 10 over 36. So 26 over 36. This one is 26 over 36. Okay. What about here? E given H. Now, E and H are independent. Why? Okay, E and H are independent because think of the first trial. You're rolling a number. It's not 5, it's not 7. For example, it's 2. So I got a 2. Doesn't really matter. Next trial is going to be like a reset. Like we're starting from scratch because 2 doesn't matter. Okay, when I roll 2, I'm just going to, okay, it's not going to end. The trial keeps going and going until I get 5 or 7. So it's resetting. The probabilities are again the same. Okay, it's all the same. The state hasn't changed. Nothing has changed. So anything goes, and 5 or 7 can still come. I'm just going to roll the dice. So I can pretend that 2 hasn't come up. It doesn't really matter. Okay, the second trial is now the first trial for me because I don't care if 2 has come up. It's not there. I don't see it. It doesn't change the outcome. So the second trial has become the first trial, which means that rolling anything other than 5 or 7 doesn't change the probability, which means that E given H is actually equal to E, probability of E. Now, from here, we have 2 probabilities of E, one on each side, left and right side, and lots of numbers. We just simplify all of them, and we get the probability of E is 2 over 5, which is 0.4. Now, This is the conditioning on the first trial approach. The second approach is actually much easier for this one, but it isn't always easy to use that one in all questions. We have talked about reduced sample space, remember? Now, in this question, there is a reduced sample space. I told you that any role other than 5 or 7 isn't important for the first trial. It's still the same in the second or the third or the n trial for any value of n. As long as the trial doesn't come up 5 or 7, all other outcomes are unimportant. So we can just remove all of them from the game. We can say that, okay, our dice is now a 10-sided dice. Well, 4 of them has 5 and 6 of them has 7. So roll it once and you will find your answer. That's it. Because I only have 4 over 36 probability for 5, 6 over 36 probability for 7, but I had 36 outcomes, or 36 different roll types, not outcomes, 12 outcomes, but with 36 types. So now I only have 10 outcomes, 2 outcomes with 10 types, or let's say. So what I have is only the 5s and 7s. The rest of them are removed from the space. So I have a reduced sample space with 10 outcomes only, where 4 of them is 5 and 6 of them is 7. So getting a 5 out of those 10 outcomes happens with only 4. So 4 over 10, which is 40%. Same answer. As you can see, I can just remove the unwanted, or let's say the ones that are not useful, all the outcomes that are not useful from the experiment. And when they are gone, I can just work with the reduced sample space easily. So what about the hats? We had hats last week. We will have hats again. This question is a bit hard to understand, hard to internalize, let's say, and hard to work out the math as well. If you want to really understand, you have to go over it a few times by yourself, but still I will just try to be as clear as possible. At a party, n men take off their hats. The hats are then mixed up and each man randomly selects one. We say that a match occurs if a man selects his own hat. What is the probability of no matches? Now, this is really hard because start with the first guy. I'm the first guy, I'm going in, picking a hat. My chance of getting my own hat is 1 over n. Okay, not getting it is n minus 1 over n. Let's say I got the second guy's hat. Now the second guy comes to the pool picking a hat. His hat is not there. He cannot pick it. So it's obvious that he's not going to pick his own hat. But whose hat does he pick? Does he pick mine, which will reset the question, or does he pick someone else's, which will just keep going? Now, this can be, let's say, defined as a loop, okay, where we are trying to find how the loop progresses. Now, let's say that Pn, okay, n different guys, Pn is equal to Pe. E is the no match situation. P1 is there is no match in the first pick. P2 is there is no match in the first 2 picks, etc. Something like that. And Pn is there is no match in all the n picks, okay, which is equal to Pe for us. We are looking for Pe, probability of E. Now, we know that we can just define this Pe on the first guy, okay? Does the first guy select his hat or not? Now, let's take a look. Pe is here. Event M is where he picks his own hat. Event M complementary is where he doesn't pick his own hat. Now, if he picks his own hat, the first guy picks his own hat, the probability of everyone picking different hats is 0 because the first one has already picked his own hat, so it's gone. This is 0 and this part will be gone. Now, what about here? I know that this part is the first guy not picking his own hat is n minus 1 over n, which is cool. And I'm looking for this part as well. This part isn't that clear right now. He hasn't picked his own hat, so what's the probability of everyone not picking his own hat? We have to get it more detailed. So think about it. As I said, the second guy, he's coming along. Which hat did the first guy pick? If he picked the second guy's hat, the second guy is not going to pick his own hat no matter what. And he can either pick the first guy's hat, and the question will reset. Instead of n guys, you will have now n minus 2 guys with the same thing. You are looking for the same thing. No one picking his own hats. Instead of n, you have n minus 2. Or he picks someone else's hat. Okay, like the third guy's hat, for example. Then when the third guy comes along, is my hat in there? That's his question. If it's not in there, he can pick the second guy's or the first guy's hat, whoever has a hat in there, I don't know. No, so the second guy's hat is already picked, first guy's hat. If he picks the first guy's hat, again, reset. The first three guys have picked each other's hats, so it's a reset. We are gonna do the calculation with n-3 from the start, okay? If he doesn't pick the second guy's hat, again, the loop keeps going. The fourth one is looking for the his own hat again, but is it in there? We don't know if the third one picked it or not. Goes and on again. So we are actually doing this in a loop, okay? They are all related to each other. And then, is the extra hat grabbed or not? This is all that's about. And we can just calculate them all and just keep going and going. Now, as you can see, we can write the probability we are looking for in this way, like a loop, okay? And then, as you can see, we can start looking for them, looking for each p-value. Just put the numbers in there. We already know that p1 is 0, because if there's only one guy and there's only one hat, then he's gonna pick his own hat, and we're done. You can do nothing about it. When there's two guys, okay, no one picking his own hat, it's 1/2, because the first guy goes and picks the second guy's hat, it's 1/2, you're done. And with 3, 4, it goes up, goes down, goes up, goes down. And with n people, we have e to the power of -1. So it's 0.368 when you calculate all of these together. But you can see this is a series. It goes and plus, minus, plus, minus, plus, minus. And we know that this is the, series of e to the power of -1. So this can easily be, summed up to this one, 0.36. Now, I told you at the start of the chapter that there was a Monty Hall problem. It was similar to a card problem, not really, similar, like let's say question-wise, but solution-wise a bit similar. Now, this is actually a very, let's say, famous problem. It's on the internet. You can find it very easily. There are lots of different explanations for it, and people still don't believe the answer, etc. So you're going to have to trust me on this one. The answer is pretty clear here. But most people do not believe the answer. Not most people, but let's say those who are not, working as, who are not familiar with statistics or mathematics or stuff like that. Okay, don't believe the answer and just, oh, it's going to have to be like this. But we're going to see what it's about. Now, we are in a game show. We are in a competition, maybe. You are picking a door. There are 3 doors. And you know that behind one of these doors is a car, and behind the other 2 are goats. So there is no prize there. There's a prize door and no prize door, 2 no prize doors. You pick a door at random. It can be the first door, it doesn't really matter. And then the game show shows you another door. This other door doesn't have a car behind it, it just has a goat. So what do? Do you change your decision? For example, you pick the first door, he showed you the second door. Do you pick the third door? Do you change your decision? Or you pick the first one, he showed you the third one. Do you pick the second one? Or do you stay? Is there a difference? Okay, is there an advantage to switching your door? This is the question. Any ideas? Would you switch or would you stay? Okay, someone doesn't, switch. What about others? Switch, 2 people switches. Okay, why would changing increase our chance? Why? Why the switch? Okay, you can think, and I will just explain it a bit. Think about it. You have 3 doors. In the first choice you're making, what's your probability of picking the right door, the car door, in the first choice you're making? One over 3, exactly. So you have 3 doors, one of them has a car. Your chance of picking the right door, the prize door, is 1 over 3. Let's stay there. We'll just go back to it later on. What about calculating the, you have to calculate something here using condition probability. What is our condition? What are we looking for here? We are looking for a way to win the game, okay? And what we want to do is, what's our probability of winning the game? For example, if we change our door or if we stay, okay? we're gonna use that one, probability of winning the game by changing the door, and then we're gonna have to condition it on if we have picked the right door or not, because it changes. If we have picked the right door at the first choice, and if we change our door, then we lose 100%. But if we pick the wrong door at our first choice and then we change, we have eliminated another wrong door because the game show host has shown it to us. So we're going to pick the right door. Again, that's a certainty. Now, we can go that way or we can go the enumeration way. Let's go with the enumeration way first. Let's say that we have picked the first door. Now, there are 3 different outcomes. The car can be in the first door, in the second door, or the third door. So the car can be here, this is one of the outcomes. The car can be here, another outcome, and the car can be here, another outcome. Now, if we pick the first door, and the game show host has shown us door 2 or 3, doesn't matter, he shows one of them, and we switch, we lose. If we stay, we win. When we pick the first door, it has a goat in it, and the car is in the second door. Then the game show host will show us the third door, because he cannot show us the second door. The car is in there. He knows when the car is. So when he shows us the goat, we can switch from door 1 to door 2, which will make us win. Or the car is in the third door, we are picking the first door, and he shows us the second door. Now, we are going to switch once again, and we pick the third door, and we're going to win. So out of all these 3 outcomes, when we switch, we win 2 times. If we don't switch, we only win 1 time. So we have to switch. Switching will make sure that we win it at least, not at least, but exactly at 66% probability. So we have to switch. This is the enumeration part. What about the notation? How can we write this? Now we have to define 2 events for this one. The first event is picking the correct door at first choice, which is C, correct door at first choice. Second event is winning after switching, the probability we are looking for, we're going to be looking for. Winning after switching, okay? We are looking for the W, winning after switching. We are looking for W, and we're going to condition W on C. As you can see, we have W here, and we are conditioning it on C. W given C times C, W given C complementary times C complementary. Now, in here, this value is 0, and this is 1/3. This value is 1, because if we didn't pick the right door, switching makes us win 1, and this value is 2/3, which is calculated as 2/3, same as enumeration. Okay? Now comes the exercises, all the exam questions. Now, these questions are so-so. They are hard ones, easy ones, you will see. And they are going to be similar to what you're going to face in the exam next week, most probably. Suppose that 30% of all houses need a paint job. Also, 15% of all houses need both a paint job and a new roof. Further, 7% of all houses that need a new roof also need new windows. It's giving us probabilities, and we're going to write them down. Let P be the probability that a randomly selected house needs a new paint job, given that it needs a new roof. What's the minimum possible value of P? Okay. Now, as you can see, 30% of all houses need a paint job. We have written it down. Okay. 15% of all houses need both a paint job and a new roof. It's intersection, so new roof and paint job together, 15%. And 7% of all houses that need a new roof, this is a given, need a new roof, also need new windows. New windows, 0.07. So let P be the probability that a randomly selected house needs a new paint job, given that it needs a new roof. Paint job given new roof. It's asking us this. Now, this one, again, we're going to use the equation from definition, can be written like this, the intersection over the condition. We already know that the intersection is 0.15. We were given this one. We are looking for the new roof probability. Now, new roof probability, again, we can just use the rest of the bias and open this up, conditioned on PJ. And we know that, we can just use the, intersection as well, but still, either, intersection or condition will work, doesn't really change the result. So we know that this part, this NR is equal to, let's write it down, P of NR is equal to P of NR and EF, is EF, no, PJ, sorry, NR and PJ plus P NR and PJ complementary. Now, NR and PJ is here. This is the intersection. So we write 0.15, sorry. And then we're going to have to find out this one. Now, NR and PJ, we already know that PJ complementary is 0.7. So this value cannot be anything greater than 0.7 because we're intersecting two sets. So the outcome cannot be greater than one set's number of elements, number of elements. So this value can be at most 0.7. Okay, we're gonna multiply it with a y is between 0 and 1, so it's gonna be something between 0 and 7. But it's at most can be 0.7 or 0.7. Now, this x value, we're looking for the minimum value of p, this one. If this x value is taken as the max value it can be, then this value will be minimum. So we take x max, to find x max, we take this value as 0.7. So we will, take x max as maximum value, which is 0.75, 0.15 plus 0.7. And then p becomes 0.15 over 0.85, which is 0.176. Now, this is the easy one. So not so easy, but still, you have to think of picking the x max. This is the only trick there. The other parts are not that hard, as long as you get used to notation. Now, the second part, assume now that you are told 50% of all houses that do not need a new paint job do need a new roof. What's the probability that a randomly selected house needs a new roof? We are looking for a new roof, okay? Yeni çatı. Now, the thing is, if, let's say, of 50% of all houses that do not need a new roof, paint job do need a new roof. The not need a paint job part is a given part. It's a condition. They need a new roof. So no paint job is given, and you're looking for a new roof, which is 0.5. Okay. What's the probability that randomly selected house needs a new roof? We are going to have to calculate a new roof part. So we already know that it's going to be calculated like this. We are conditioning on it, and we already know that this part is 0.15 because this part, because this part is equal to this one. Okay, because it's equal to this one anyways. So we are going to look for this one. Now, we already know that this is 0.5. It's given in this part of the question. And we already know that this is 0.7. Just multiply them and add them together, and we're going to get 0.5 anyways. And second one. Now, this is a proof question, which you're not going to face, most probably, because, face it, books are open, Google is open, proof questions are too easy to find solution to, so we will not ask anything theoretical. But still, let's take a look at it as an exercise. Prove that an evidence E increases the probability that event A occurs. If and only if counter evidence E complementary decreases the probability that event A occurs. In other words, A given E is greater than A given E complementary is less than A. So this is an if and only if situation. We have to start with one part and reach the other part. Now, all you have to do is that when you take a look at the differences, they both have PAs, but one of them is E, the other one is E complementary. So we have to change this E into E complementary. We have to make sure that it becomes E complementary, all the E's in the, equation. Now, we start with the conditional probability, definition formula. We remove this condition value, condition operator, and then we start simplifying, getting all the E values turned into E complementary. You can easily keep track of this, operations of these lines easily, and you will see that at the end of these lines, you get the right-hand side. And then, as it's if and only if, two ways, the arrow is two ways, you have to start with this right-hand side and get to the left-hand one. And again, you have E complementary, you have to change E complementary into E, which is shorter than the first one. And then you get the first result, the left-hand side result as well. As I said, this isn't that hard to keep track of, but you have to know that you are going somewhere, how you are going there to prove stuff like that. The going itself isn't that hard, but you have to know how to go there. Now, third question. Suppose you are taking a multiple choice test with C choices for each question. In answering a question on this test, the probability that you know the answer is P. So you may not know the answer. If you don't know the answer, you choose one of the C choices at random. You just pick a, pick one of the choices. There's nothing you can do about it. You don't know the answer, so you have to pick one of them. What's the probability that you knew the answer to the set question, given that you answered it correctly? Now, we have to define two events here again. The event that you know the question, the answer to the question, which I'm going to name Q, and the event that your answer to the question is correct. These are two different events. Knowing the question and answering it correctly are different because you can still answer the question correctly without knowing the answer. You're just going to pick one of those, choices, one of the multiple choices. So there is a possibility of answering the question correctly without knowing the answer. Then it's asking us, Q given C. We know that the answer is correct. So what's the probability that we already knew the answer to the question? Q given C. Well, we have to use the, Bayes' formula once again. We can just open it up and put everything in its place. Let's take a look. Q given C, okay. Q intersection C over C. C given Q times PQ. And then this is the same thing anyway. And now we are just opening up C, okay, conditioning C on Q. So we are gonna have to see the given Q and given Q complementary parts anyway. And now we will just write all the probability values in them. For example, for the first part, C given Q. Okay, you know the answer. The probability of answering it correctly is 1 because you know the answer. And then knowing, answering it correctly in any given question, P. Knowing the answer, knowing the answer in any given question is P. Again, this is the same 1 times P. And in here, you don't know the answer and you want to answer it correctly. This is 1 over C because you're going to pick one of the multiple choices. And then in here, you have 1 minus P because you don't know the answer to that question. When you, simplify all these, you get this outcome, C times P over CP plus 1 minus P. Not, that hard, not that simple, but it's doable. As long as you know how to apply the, Bayes formula, how the transformation happens in there. Exercise 4. Now, this one is harder, much harder than the previous ones because we have more events and more values to calculate in here. This is actually one of the hardest, in my opinion, not to, model, but to solve, I would say. But still hard enough. A student must answer at least 7 questions out of 10 questions in a final exam to pass the course. Okay, you need to pass the course. You need to answer at least 7 questions. She will answer each question correctly with probability 0.80 if she studies on the day before the exam. All right, and with probability 0.40 if she doesn't study on the day before the exam. So if you study, you have a higher chance of answering the question correctly, which is expected. However, if on the day before the exam the weather is good, she will study with probability 0.3. Okay, if there's a good weather, she will just go out and have fun. And if it's bad, she will study with probability 0.60. Okay, if it's rainy, she's gonna stay in and study. Good and bad weather probabilities are equal. Okay, if she passes the course, what's the probability that she studied on the day before the exam? Now, if she passes the course, passing the course is an event. So we have the, let's go see the C event, passing the course event. And now we have studying before, the day before, the S event. Let's say S is that we studied before, the day before the exam. And we need more events though. We need the weather is good event. Let's call it G, okay? The event is that says that the weather is good that day, the day before the exam. Now, we are looking for the probability that he or she has studied if she has passed the exam, the course. So S given C. We are looking for S given C. Now, S given C can just be opened up, with transform with the Bayes formula anyway. And when we transform it, we get this part. Now, as you can see, we have just transformed it, use the Bayes formulation. You should be, accustomed to it by now. This is the 4th or 5th time we're seeing it. But still, this is not enough because S itself, the S value itself, well, this is not a simple value. You have to find out what S is. And S is dependent on G, another event. So we have to calculate S dependent on G. So we will just open it up, transform it into a value with G. As you can see, conditioning it on G, conditioning S on G. If the weather is good, my chance of studying, my probability of studying. If the weather is bad, my probability of studying. Again, I'm going to do this for all the S values. As you can see, there is an S value here and there is an S complementary value here. And then we have to calculate all these values, everything in here. Now, surprisingly, these larger brackets is much easier to calculate than this one, because this one is dependent on the number of correct answers you have given, and it can be 7, 8, 9, or 10. So you have 4 different scenarios to calculate for, which is not easy in the exam. So you have to use a calculator or just leave it like that in the most obvious way possible, of course. But these values, the ones that show the probability of studying, is easy depending on the day at least, because they can just be multiplied and then summed. It's quite easy actually. But it says that at the end there's a 93% chance that he or she has studied before the exam if he or she has passed the course. Another one now, another question. We have 5 white and 10 black balls. A fair die is rolled, and that number of balls is randomly chosen from the urn. Okay, we are going to pick balls, but we are rolling a die for that one. Okay, what's the probability that all the balls selected are white? Now, again, we have to define the events, but we have lots of events here. Why? I'm going to define Ri. Ri is the result of the I. So if it's R1, 1 has come up with the roll, with the dice. If it's R2, 2 has come up with the door. If it's R3, 3 has come up with the dice, etc., etc., etc. And these are 6 different events. And there is W. All balls are drawn are white. This is simple enough. So what I'm looking for is the probability that all of the balls are white. So I have to find out which roll has come, and then I can, find out what PW is, the probability of W is, because W is dependent on R, and R has 6 different values, mutually exclusive 6 different values. So we have to break W into 6 different terms, okay? And each of these terms will be dependent on the value of R. So if it's R is 1, the roll has come up 1. If R is 2, roll has come up 2, etc. So as you can see here, we are looking for PW, and it's dependent on RI. Now, for RI, it's always 1 over 6, because all the values of the dice has a probability of 1 over 6 to come up. Nothing, no surprises there. But with W given RI, we have this formula. Now, we are trying to pick I white balls out of 5 white balls, and I balls out of 15 sample space. Now, as long as I is less than 6, we are okay. If I is 6, this one becomes 0, because you cannot pick 6 out of 5 balls, so it goes off. So with 1, when I is equal to 1, we have this formula, okay? And then 5 choose 1, then 15 choose 1. If we have I is equal to 2, then we have 5 choose 2, 15 choose 2, etc. And it goes on like this. Now, we know that this is already 0, we don't need this one. And then we calculate all of these values and see that PW, the probability of picking all white balls, is 5 over 66. Now, just a little below 1 over 11. But still, it's too little. But we are done with part A. Part B asks us, what's the condition probability that the die landed on 3 if all the balls selected are white? Now, we are looking for R3 given W. Now, this is a new, probability. We are looking for R3 given W. We can just write it, we can just transform it with W given R3, because we already know what W given R3 is. We have found it in the previous part of the question here, over here. So we already know what this is, and we can just use this one over here. And we already know what the probability of getting all white balls is. We have already found it in the first part as well, 5 over 66. We will just write these values and divide them by each other. And then we're going to get 22 over 455. Now, this part, the tricky part, is seeing that the die has 6 different results that it can come up with. So we have to define 6 different events for it, so that we can condition W on these events, 6 R events. Okay, this is the tricky part there. What about the next question? Now, consider a parallel system of 2 components. As I said before, we have lots of system questions in there. The first component functions with probability 0.95, and if it functions, the second also functions with probability 0.95. If the first has failed, the second functions with probability 0.70 due to heavier load on a single component. Okay, what's the probability that the second component functions? Now we have 2 events, F and S. F shows that the first component functions, S shows that the second component functions. Now, we are being asked in the first one, value of S, okay? But S is dependent on F, so we can just condition S on F, which is done like this, as you can see here. We are going to condition S on F. The probability of S given F times PF, the probability of S given F complementary times PF complementary. Now, from here, we can just write the values. S given F, if the first component is working, then the second component works with 95 probability. So I'm going to have 0.95 here. The probability of the first one, the probability of the first one working is 0.95, so it's written over here. The probability of the second one working, if the first one is not, well, 0.70, we already know that one, write it over here. The probability of the first one not working is 0.05. So just multiply them and add them together, 0.94, give or take. So 94% chance that the second component is working. What about part B? What's the reliability of the system? Now, reliability of the system means that they work because they are, parallel systems. So at least one of them has to work. If they are both not working, then the system fails. But if at least one of them is working, then the system works. There are no problems there. So what? How do we do that? Easy. We already know that we are looking for this one, both of them to fail. Okay, we want both of them to fail, so we can, subtract it from one. So instead of writing this, we can write this one, because this is equal to this one. We know that from the definition of, condition probability. Oh my God. From the definition, we already know that these two are equal values. So we can just find this one. We already have found this one, actually. We already know that FC is equal to 0.05. And SC, when FC, okay. S given FC was 0.70. So SC, S complementary given F complementary is 0.30. So we just multiply them and subtract them from 1. So we get 0.99, 99% chance of failure. Okay, no, sorry, working capacity. Reliability is 99%. And then C, if the second component does not function, what's the probability that the first one does? Okay. Now, F given S complementary. The second one is not functional, but we're looking for the, probability that the first one does. So we're just going to use the, definition again, formula again, and put everything in there. And we're going to find 0.76. It's not that hard. After A and B, this is actually pretty easy because we already know all the answers for these, values for these terms. So 0.76 is the answer for the C part because we have already opened it up and put everything in its place. That's it. Exercise 7. This one is a bit harder than the previous one. Again, we have systems, but 2 of them now. And each system has 4 components. And in the first system, 2 components are parallel in 2 subsystems, which are in a series. As you can see, 1 and 2 are parallel, which is series with the 3 and 4 parallel system. Now, in the second one, in the system B, 1 and 3 are series, 2 and 4 are series, but they are parallel altogether. So, which of these systems has a higher reliability? Now, you can guess that one just by looking at it, and you're going to say A, which is correct, because we expect A to be more reliable. But still, we're going to have to see. We're going to have to calculate. Now, as we are talking about reliability, we are talking about the chance of working, okay? No malfunctions, no failures. We are working. So, in here, you can see IM. Component I of system M functions properly. This is the event. So this is the sub component. Subsystem of J of system M works. That can be really hard to remember, but still. Reliability of A means that system A works. Okay. Then we are looking for sub 1A and sub 2A, both subsystems working. Because as you can see in the first one, both of them has to work. Okay. If both of them works, then the system works. So we're going to have to take a look into how they don't work. So if one of the subsystems do not work, then we're done. Okay, for the first one to not work, both 1 and 2 shouldn't work. So 1 minus probability of 1, 1 minus probability of 2, again, 1 minus all of them, multiplication of them. So this is where the first component doesn't work. This is where the second component doesn't work. We multiply them, so both of them doesn't work. Okay, we subtract that from 1, so at least one of them works, which means the subsystem works at the end. Do the same thing for the second subsystem. In here, you can see that the third component isn't working, the fourth component isn't working. When we multiply them, they are both not working. So when we subtract that from 1, at least one of them is working. So both subsystems are working right now. We just put the numbers in there, and we got 0.98, 98%. For B, it's the same, but a bit different. We need to make sure that at least one of the subsystems work, 1 or 2. Okay, sub 1 plus sub 2 minus both of them working, because this is union, not an intersection. So A plus B minus A and B. So we have to make sure that sub 1B works. This is 1 and 3. Or sub 2B works. This is 2 and 4. Or both of them work. This is multiplied by each other. As you can see, we can just write the numbers in there. It's easy to write. And we get 0.96%. 96% of reliability. Now, what about B? Part B asks us, if we know that system A is working, okay, what's the probability test which is 1 and 4 are functioning properly? System is working, okay. We already know the system works with 98% probability. So we know that reliability is this one. This is something we know. So system A works. This is the given. Components 1 and 4 are working. This is what we're looking for, the probability we're looking for. We can just write the, Bayes or the definition part. We already know the value for system A works. We have found it in part A. What about here? This one. When 1 and 4 works, what's the probability that system A works? When 1 and 4 works, let's take a look. When 1 and 4 works, system A works 100%, because there is a way from the first, from input to output. So you can just go from like this. So when 1 and 4 works, system A definitely works, no problem. So this is 1. The probability of 1 and 4 working, 0.9 to the power of 2. So we can just divide this by 2, we will get 82.64. What about C? C, okay, system doesn't work. The system doesn't work. 1 and 4 working for part B. Okay, again, we're gonna just use the definition and just transform this into the longer side. We already know the probability that system B doesn't work, because we know the probability that system B works, the reliability. So we just subtract the reliability from 1. It's going to be easy, as you can see. In here, though, if 1 and 4 are not working, okay, we know that these two are not working, and we want system B to not work. Okay, let's take a look then. When 1 and 4 are not working, doesn't even matter, does it? No, sorry, 1 and 4 are working. We want system 4 to not work when 1 and 4 are working. So if 1 and 4 are working, then the system should fail if and only if 2 and 3 are both failing. Okay, so we're going to have to check to see 2 and 3, the complementary of 2 and 3, they are not working. So it's 0.1 to the power of 2. And then we can just multiply everything and simplify it into 0.22. Doing the math here, just using calculator, isn't really that hard, so you can do all of these yourselves. And I advise you to do it yourself at least once to see the calculations are correct and that you can make them easily. But the most important part with these types of questions is always the modeling part, the event part, writing the events and then writing the formulations that go with the events. And here comes the question that is heavily dependent on that one. Now, I toss a coin repeatedly. This is an old exam question that I have asked at least 3 or 4 times, maybe 5 times, I have no idea. I toss a coin repeatedly. The coin is unfair and the probability of coming off heads is P. The game ends the first time that 2 consecutive heads or 2 consecutive tails are observed. I win if HH is observed and lose if TT is observed. For example, if the outcome is HT, HTT, I lose. On the other hand, if the outcome is HT, HT, HH, I win. Find the probability that I win in terms of P. Now, this one is the perfect example of conditioning on the first trial. Okay, because contrary to the example we have seen with the dice, 5 and 7 and this, we cannot reduce the sample space that easily. It's not done. It can't be done. It was very easy with the dice, but in here it's not that easy because the effect of winning is very different. We are looking for 2 H's, 2 heads consecutive heads to win or 2 consecutive tails to lose. So we have to condition on the first trial, and now we're gonna loop on each other, which you're gonna see in a second. So if we're gonna condition on the first event, then we're looking for 3 events. The first one is the event that I win. I'm looking for the event that I win because it's looking for the probability that I win. Okay, let's give it W. And then there is T1. First toss is tails. And then there is T2, H1. First toss is heads. There are T2, H2, etc. But the first one is the important one right now. We are looking for the probability that I win, and I'm going to condition on the first toss. Okay, so I either have tail or head, doesn't really matter. Now we know that the probability of winning can be conditioned on the probability of rolling or flipping a head on the first roll or flipping a tail on the first roll. Okay, first flip, whatever. So I can just say that W given H1 times H1, W given T1 times T1. We already know that one. Then I have to find out values for these ones. But probability of getting a head on the first trial is P. You already know that. It's okay, it's the same everywhere. Probability of not getting a head or getting a tail is 1 minus P. It's okay as well. But these terms aren't that easy to define. We have to check them one by one. Let's start with W given H1. Think about it. You have rolled, you have flipped, and it comes up head on the first trial. Okay, I have a head on the first trial. To win, I need 2 consecutive heads. So if I flip another head, if I get another head, I win. So there's a P chance, P probability that I win at that moment, at the second trial, and it's done. But if I flip and it comes at tails, then the chance is gone. I have to keep flipping till I get 2 heads in a row. So if I get to win with the probability of P, I can just write P here. But if I get a tail, which is 1 minus P, then I will have to start again, just like in the previous example, okay? I get a tail, okay? Think about it like this. There are 2 different, let me just show you. 2 different, come on. We start with a tail, or we start with a head and then get a tail. Now, in both of these situations, in those 2 scenarios, I'm going to roll or flip the second time here, the third time here, but still I'm going to flip again. Is there a difference between those 2 for my ability to win, for my probability to win? Is there a difference between those 2? No, there isn't, because I need 2 heads, and I lose instantly if I get a tail in both of them, and if I get a head, I need another head to win. So these 2 scenarios are exactly the same. So the probability of winning here is the same as probability of winning here. So if I flip tails, then I will have the same probability with the first scenario, which was given here already, like this one. All right. What about this one? When we start with a tail. When we start with a tail, I have to flip a head, because if I flip another tail, if another tail comes up, I lose instantly. So with probability P, I can be having this scenario. But this scenario is the same as this one as well. There is no difference between those 2, because they all end up with H, and they are looking for another H, another head to win. So this one with probability P becomes this one. So now I have 2 formulas that are related to each other with 2 unknowns. So I can just take one of them and put it into the other, like a loop. And then we will just solve it, like as if we are solving a linear equation. Now, when I put this one into this one, I can find out that the probability that I win the game if I start with a head, to condition that given that I start with a head, is P over 1 minus P plus P squared. So I already know that this one here, as you can see, this one, let's just draw them, as you can see. Okay, why is it? As you can see, this one is equal to this one right here. So when I multiply this with a P, I will get W given T1, which is over here. And then I will take both of these values and put it in the original equation. And I will get this polynomial with the 3rd degree. So yeah, it's not easy to, you know, reduce the sample space and then go from there. You cannot find this type of, you know, equation from reducing the sample space. It's not easy. I don't think you can do it here. I haven't actually tried, but I don't advise you try as well. So, any questions?